Thank you very much, Toby. Thank you, Admiral Richardson. Really pleasure to have you all with us this morning. It's something we've been looking forward to for a very long time. It's the first time that we do this event in Texas. We have done it in Washington, D.C., slightly different audience then, but this is a wonderful occasion for us. So thank you all for coming. I wanted to segue a little bit from what Admiral Richardson just said about these security aspects of it. I mean, history teaches us that great naval powers are also great maritime powers. And that sustainable naval power must be supported by a commercial supply chain. It must be supported by a market that's there to support it, that isn't a tenuous link that the naval forces have to hold up all by themselves. And you mentioned China, and that's really the greatest shipbuilding nation in the world today. Of all these new green ships, these supposedly green ships that are being built, in the last 6 months, they've taken over 75% of all global orders, leaving everyone behind. The foundations for them being able to push this forward is absolutely in place. And the one thing that's really missing is that maritime nuclear technology that they are, fortunately for us, behind. So we have this opportunity now in the next 4 years to demonstrate that this is where we can do it. So I want to just set out for you this morning a very pragmatic approach to how this is done, because this is not just about the technology. It's about how we create the conditions for that technology to function inside a complete program. The Naval Nuclear Propulsion Program is one of quality, of safety. It's a culture that encompasses every single aspect of development of technology, of engineering, of building, of operation, of servicing, maintaining, and eventually also decommissioning. And this is something that we need to do on the civilian side. So a clear demarcation, I think, where we have a strong fence with military on one side, civilian commercial on the other, but the safety and the quality standards are very much the same, come from the same point. So Core Power's mission is to get this done. And we have made an awful lot of progress over these last few years, and I wanted to just talk you through who we are and what we do and how we approach this. We're a private company. We are just over 6 years old, although we've been more than a decade in the making. We are supported currently by over 65 shareholders from the global shipping industry. And they are big ship owners, they are big shipyards, they are the shipping banks, they are the big trading houses, the cargo interests, and they are the big family offices that deal with the global fleet through generations. Multi-generational investors that are looking for the next stage of this industry. Shipping is the second oldest profession in the world, despite what anybody else might say, and it's going to be that for a long time. This program, we're calling it the Liberty Program. It's a Maritime Civil Nuclear Program, which is a bit of a handful, but we're calling it the Liberty Program because at the end of the day, this is the thing that will set this market, set the supply chains and the logistics and the security aspects that Admiral Richardson talked about, set us free from that hegemony that is now being created by the Chinese shipping industry. We're doing it also because the size of the prize is quite something. We've identified between now and 2060, so that's 35 years to be fair, but between now and 2060, as far ahead as we can see, a $5.6 trillion market opportunity in supply chain integration, in manufacturing, in operations, and in sales. It is quite something. The way we achieve this is really combining the best of what maritime can offer with the magic of new nuclear. That's the headline on this. And that creates two massive gaps in the market that we can start filling with these technologies. The first one is, of course, in order to be able to scale difficult and complex new technologies and constructions into market, we must move to modularity. Modularity is the solution to this. When we build skyscrapers today, we're not building one skyscraper, we're building 100 single-story buildings on top of each other inside a frame. Modularity is how it gets us They're on time and on budget. Shipyards are experts at this. We have our friends from Korea, from Hyundai Heavy Industries in the room here today talking about how they're doing this. And those critical partnerships that the United States and us as an organization here and in Europe need those partnerships to be able to create, if you like, that base for it. So Korea and Japan are critical partners to this. Floating nuclear power plants and nuclear-powered ships, two distinct, separate sectors with common engineering, common technology in the middle, using shipyard manufacturing to deliver nuclear on time and on budget to industrial customers. That's the first time that would ever happen. And the ability, as Admiral Richardson pointed out, to create a fleet of energy-resilient nuclear-powered ships that changes the value chains of global trade, of how we move things around. The timeline for all of this is that an order book is in the process of being formed, which really gets announced from 2028 forward. That's 3 short years from now. 3 short years from this year is when that order book starts to materialize. The delivery of that order book, of course, is something that takes time. Bureaucracy is one of those things that can stand in the way of new developments here. But really in the mid-30s, we expect to see scaling of this technology moving forward. Could I have the next slide, please? Floating nuclear power plants. People talk about them, but what do they really look like? They can look like an awful lot of different things, but they're actually quite small. Here you see a floating nuclear power plant delivering about 70 to 80 megawatts electric from a single reactor straight to shore, sitting in a port. It's about 160 meters long, it's about 35 meters wide, it has a 6-7 meter draft, and weighs about 25,000 tons. It is tiny. And it sits securely in a location either in a port, a waterway, or a nearshore environment, providing that resilient energy directly to customers. This is something that can be delivered on time and on budget, on a specific date, at an agreed price, directly to a customer, anywhere from a location where it's manufactured. There are 300 ports in the United States that need to be electrified in the next 10 years. Here is a solution that fits really well with the smallest footprint and absolutely no environmental impact at all. This is a $2.6 trillion market between now and 2060. The Russians are doing it. You guys here in America did it back in the 60s. We had them at the Panama Canal, powering the expansion of the canal in the 1960s. It works beautifully. I want to go back over the reason why these FNPPs, floating nuclear power plants, are so critical. And it really comes down to a few things, right? How do you buy nuclear? Unless you're a regulated utility with specific land authorization and the experience to build nuclear power plants, how do you actually buy this stuff? How do the big data companies, the AI companies, how do oil and gas, how do heavy industry and manufacturing get nuclear? Well, you have to get it from your utility. Here is an opportunity to partner with these utilities or even create the opportunity yourself to operate small modular nuclear power plants, delivered on time and delivered on budget. That is a first, that's a world first, and this is the way that we can unlock that promise. Small modular reactors is what everyone talks about. The reactors themselves are always small, they're always modular, and they're always reactors. It is just what it is. The hard thing about delivering nuclear is delivering the power plant. So we don't think it's about small modular reactors, we think it's about small modular power plants. Can we deliver that as a full product, like you would deliver an aircraft, or you would deliver a complex piece of machinery that's serially produced as a product to market? These are all identical, can be swapped. 65% of all human activity happens on the coast, and that's really where the market opportunity for this comes from. You take the OECD with the United States at its center, you take the European Union, you take your friendly neighbors to the north and south, you've got a massive market opportunity here that can be then scaled beyond that as we go. Nuclear-powered ships. Nuclear-powered ships are a little bit more complex in the sense that they are completely mobile. Mobile reactors is a hard thing to do when you haven't got a national state behind you. And that is what we're now unlocking, and that's what's changing with this market. It's not so much about the environmental impact of shipping. It's often said that shipping produces about 3% of global greenhouse gas emissions and that we must stop. The United Nations has said to the shipping industry and mandated that we cut 70% of our emissions by 2040. That is an unsurmountable challenge of scale. And if it's about decarbonization, we could move down the road of using synthetic fuels and using other ways to power ships, but the economics of this don't work. Shipping is a cutthroat, uber-capitalist industry that needs an economic case for this. And the only thing that can compete with the reliability of fossil fuels and the waste stream for the oil and gas industry, which is effectively what the shipping industry uses to power the big diesel engines, is nuclear energy. The only thing that can give you the oomph for these ships. Between now and from 2035 onwards, there are 12,500 large ships that must be replaced due to old age. So 2035, 2040. 2040, 70% need to be reduced. 2035 onwards, 12,500 ships must be replaced from old age. And they cannot be emitting. The only way to do this is with nuclear. So we need that new nuclear technology that unlocks that market opportunity and creates that new market. And that is something that we cannot cede to the competition. We have to do that ourselves. That's what this is about. Take out of those 12,500, 7,000 ships only out of the global fleet of 65,000 consume more than 50% of all marine fuels consumed in the world today. These are the largest container ships, bulkers, tankers, car carriers, etc. 7,000 ships. We replace those by 2040, and there's a very large portion of them will have to be replaced by 2040, we have the market. We know that nuclear works really well at sea. As was demonstrated, the Naval Nuclear Propulsion Program has shown this since the 1950s. It is a perfect solution, but the problem we have is that the technologies that are used by the Navy, the ones that are originally talked about as the ones used on submarines and aircraft carriers, they cannot be used in the commercial market. And it's not because of safety. It's not because of public concerns. It's not because of some environmental disaster potential around them. It is because we can't insure them. It's as simple as that. We cannot insure a commercial vessel powered by a naval reactor going into a port. We can insure it at sea, but we can't insure them in ports. And when we can't insure them in ports, we cannot go into ports. And when we cannot go into ports, well, there is no point having a ship. And that's the showstopper. It's as simple as that. So what we need is a technology that we can commercially insure on a mobile platform that moves in and out of the jurisdictions of the countries that are prepared to take them as signatories to that insurance convention that's now being developed. But in order to do that, in order to convince the entire market and all the ports and all the people and all of the stakeholders in this that we have to do, that we have the means to be able to create that condition for an insurable technology and deploy it where we want to deploy it, we must have this end-to-end quality program, this Maritime Civil Nuclear Program that I'm setting out for there. We're calling it Liberty. It's the end-to-end from R&D all the way through to decommissioning. The highest quality standards, the highest safety standards, the highest standards of integrity in every single aspect of this is critical to it. We need a regulatory framework. That's happening already. I'll talk about that later. And we need a social contract with the public. Those regulatory standards and that end-to-end quality regime, that integrity of the program is what creates the conditions for that social contract. We don't have to convince everybody that we can do this, but we need to convince those where this starts. The ports, which will take the first ships, the corridors in which they will trade, the customers that will use them, the receivers that will take the cargoes that come off these ships. That's the key thing. Insurance, social contract. Next slide, please. The key criteria we need to meet in order to get this done is we need that insurance solved and The simplest way to approach the insurability is to shrink the emergency preparedness zone around the reactor down to a point where you can insure inside that zone. That's how it works for large nuclear power plants. That's how it works for small modular reactors. That's how it should work at sea. If we can shrink the emergency preparedness down to the boundary of the hull, really there is no concern outside of that, and that is fully insurable. And we have the insurance industry stepping up to do that. So shrinking the EPZ is a critical thing, down as low as possible. We need to look at safeguards. The safeguards is basically the early detection of diversion of nuclear material if anyone was going to get their hands on anything that was in these reactors. Now, that's by design, it is by system design, and it is by technology as well. Safeguards is a critical thing for us to be able to do, but one of the most important parts of this is not refueling reactors in ports. Opening reactors, taking spent fuel out and putting fresh fuel in, handling that fuel outside of the reactor core causes concern for safeguards. Long fuel cycles, technologies that can run 10, 20, possibly as high as 30 years without refueling, changes everything when it comes to that. Safety, of course, is important. Nuclear is incredibly safe as it is. I spoke to one of the big nuclear risk insurers in London last week, and he said, when I asked him if there was any actuarial evidence, any actuarial data that we could use to create, if you like, a sort of model for how you would insure nuclear ships, he told me, we don't have any actuarial data. It doesn't exist because we haven't paid a claim. What do you mean you haven't paid a claim? Well, we haven't had a claim, I meant. So you literally have an industry here which is insured to the eyeballs and that doesn't usually pay out any claims because there aren't any. The safety track record of this industry is enormous, but we must maintain that safety track record through this program. It's absolutely critical. And then lastly, of course, the criteria you must meet is the economic criteria. If this is too expensive, just like hydrogen, just like ammonia, just like methanol is going to be, we are not going to get there. It's going to have to be economical, and the way to take small reactors, which are by nature more expensive than big reactors, because you don't have the economy of scale, is you get the economy of numbers through large number in production. And that's really the solution to this. That order book that goes beyond 20, 25, 30 units in the first batch creates that nth of a kind cost curve that can replicate that economy of numbers for economy of scale. Next slide, please. 5 technologies are available to us. On the left, you see the advanced light water reactor, the naval reactor. We have lead-cooled fast reactors, high-temperature gas reactors, heat pipe reactors, and molten salt reactors. We apply the criteria, the insurance criteria, the safeguards criteria, the safety criteria, and the economic criteria across those critical characteristics of those technologies, and the further to the right you go, the better that fit is. And we see that with the reactors operated by the Navy, perfect as they are for the Navy, cannot be used, and you can see they don't meet hardly any of our criteria we need for maritime. Lead-cooled fast reactors, not that much better. High-temperature gas reactors, we're getting there. Heat pipe reactors, we're almost there. It's a great new way of doing it, but they tend to be quite small. And then you've got the molten salt reactors, in particular the fast spectrum molten salt reactors, which kind of blows this thing wide open because it meets all the criteria almost perfectly. Liquid-filled reactor, fast spectrum, 20 to 30 year fuel cycle that we could run on ships that would provide all of these, meet all these criteria and these benefits. And that's really the analysis that everyone needs to go away and think about. There are many other criteria you can apply, but really looking at this from a sort of technological, logical technological perspective is the way that we get there. Next slide, please. That molten chloride fast reactor, the MCFR, that molten salt reactor in the fast spectrum, we're calling it the ideal marine reactor. Now, when something is ideal and when something is almost close to perfect fit for what you want, it's obviously also going to be very hard to build. No one's ever built one of these before. It is the world's first development of a fast-spectrum molten salt reactor. And it's happening now here in the United States. At Idaho National Laboratory, the first small-scale machine is in the process of being installed and built so that we can demonstrate this. It's going to happen, has to happen, in the next 4 years. We meet these criteria really by working through the various cases. The safety case for a liquid-fueled reactor is that it can't melt down. It's operating in a meltdown state. You can't have a loss of coolant accident in this because you can't lose the coolant. You have an incredible efficiency in the burn-up of the energy inside that fuel, and you're moving the needle from low, fairly low efficiency in current conventional reactors to the other end of the spectrum, and have, as a result, a very long fuel cycle. 20 full power years in a ship is roughly 30 years of operation. It's durable. We can filter the fuel. It's liquid. It's moving around the reactor. We can filter out the impurities that we don't want in there. And we can keep control the spiciness of the soup, if you like, to keep it going for a very long time. Potentially also use it from generation to generation in new ships. The fuel moves into next generation ships because of that characteristic. We believe that the reliability of a system that has very few moving parts can be set to a 5 or 10-year maintenance cycle, corresponding with special surveys. And critically, we can ensure it. It's a low-pressure system that has a small emergency planning zone. Not quite defined what that is yet, but we believe it's going to be small enough for us to get good, if you like, affordable insurance for the ships that use these. And of course, being a fast-spectrum reactor, it consumes a lot more of the actual energy in the fuel that it has and leaves much less waste than conventional reactors. So the sustainability is strong. This is being built in a very strong partnership between TerraPower, phenomenal organization in the Pacific Northwest of this country that has some of the smartest people that I've ever met building this technology. Southern Company down in Georgia and the southeastern quadrant of this country as the utility sort of operator of the machines. Hyundai Heavy Industry is the world's largest shipbuilder, individual shipbuilder at the moment, and of course us, Core Power, who's driving this program forward. It's a power of partnerships that's building this technology. Next slide, please. Program comes in 3 phases. The first phase of this program is technology development, product development, and bringing it to market through licensing. And as you can see, if you can see from this, you have the technology sitting right in the middle of it. It's not just the actual reactor technology, it's the interfaces, it's the solutions design, it's the whole packaging of this technology so that you can lift it in as a power pack into floating nuclear power plants and nuclear-powered ships. On the left, nuclear-powered ships, 3 key things we need to solve for. We need to solve their access to ports, and we do that through the insurability, technology leading to the insurability of ships in ports. Second important thing is export controls. We have, as a result of the only existing nuclear propulsion program being the naval one, things are primarily under military export controls. Military export controls, also known as ITAR, is a difficult one to deal with. It's not appropriate for the civilian market, and we need that separated so that maritime civil nuclear propulsion sits on the commercial side under the Department of Commerce, not under the Department of Defense. And of course, safeguards, very important. For the floating nuclear power plants that you see on the right, the 3 critical things we need to be able to do is we need to be able to provide localized energy security, reliable energy security, so whatever the weather, you've got that power. We need to be able to show time and economics. Can we deliver on time? Can we deliver at the price that we've said? And modular construction is the way that we get there. And then, of course, scalability. Can we keep making the same product again and again and again in large numbers and get better at it, better quality assurance, faster learning curve, and create a better product, like we do with everything that we make in a mass-assembled environment. Can we do that with nuclear power plants? Well, yes, this is how we do it. Next slide, please. Export controls, I'm going to go back to just slightly because it is a very important part of this. We have ITAR on one side, we have the EAR on the other. And it's critically important in these next few years that the US government organizes the clarification of ITAR, the International Traffic in Arms Regulation, the US munitions list, as being one that defines what naval nuclear propulsion is and looks after and protects the naval nuclear propulsion program, whilst on the civilian side, which involves the nuclear regulator, the Nuclear Regulatory Commission, the US Coast Guard, Department of Commerce, etc., a very robust set of, or a regime rather, that can look after the maritime civil nuclear propulsion. We believe that there is consensus amongst the critical people that need to get this done in the US government, and a campaign must be run now over these next few years to make sure that this is done. It's not easy, but it can be done. Next slide, please. Phase 2 of the program, once that product has been brought to market, is really building out that supply chain and the workforce. So that work has already started. Building out the workforce, building out the supply chain, creating the conditions for this to happen. It's finance, it's workforce, it's making sure that the final parts of the regulations come together so that we can then set up the manufacturing base, the shipyard that's going to fit out these vessels. That'll be here in this country, by the way. We're looking for sites. How we finance this through export credit guarantees, to debt from finance, from equity, from joint venture type arrangements, etc. There is a large scale amount of funding both available and that has to be organized into each one of these. And of course the workforce, setting up that program of education, of training, not just of seafarers and crew members, but of those that are going to be the engineers and the managers and the operators of the various technologies we have here. We believe this is a career opportunity for a next generation of STEM students and engineers to come into a market which is potentially going to be of very high impact. Regulations, well, that's sometimes out of our hands, and what we've done, instead of trying to influence regulations as a private company, we've set up and joined forces with compatriots in the market and set up an NGO called NEMO, the Nuclear Energy Maritime Organization. Now has close to 50 members after not even a year of operation, and is in the process of getting NGO status at the critical UN agencies that manage the regulations for nuclear and maritime. Next slide, please. That factory, that home yard, that place where we will set this up is the one where we would have the manufacturing of reactors, the synthesis of the fuel, the creation, if you like, the fitting out of the power pack that gets installed in ships and floating nuclear power plants. Those, without those power packs, will then be manufactured and put together in shipyards overseas. At least initially. There's no real shipbuilding industry in this country that can support this. So Korea, Japan, potentially Europe. Those are towed to the United States, to this yard that's fitted out here. They are placed under licensing and regulations in the United States. A US flag is put on those ships, and the licensing is done for the FNPPs. And those are then moved out from that. That's also where they will come back to. This yard is where these ships and these FNPPs will come back for refueling, for maintenance, for repairs, for servicing, and eventually also for decommissioning. It's the home port, if you like, of a fleet of FNPPs that can operate in ports around in the area where that yard is and can be replaced instead of refueled where they're located. They can be replaced with identical power stations that are towed into place, and then the one that needs to be refueled is then towed back here, refueled, maintained, etc., before deployed in the next site. So fleet optimization of nuclear power in a completely different way than we've thought about it before. Same with nuclear-powered ships, of course, sailing around with a US flag on board. Next slide, please. The academy and the workforce for this, we've already started. We have an academic resource program already started with key universities, Cambridge, MIT, large number of universities around Europe and the United Kingdom that are now joining this program, or students are joining this program to get support for their studies in maritime nuclear, floating nuclear, things to do with the regulation, technology, etc. We have large number of students now already enrolled, and we expect that program to grow. They become the interns, that become the graduates, that become the ones that come into this program. It's an early start to something that I think will grow into thousands over the next 5 to 6 years. We have the Convoy Executive Program for those that are customers of this technology, corporations, those that are executives like yourselves, that are looking at how we're going to get this technology incorporated into our operations, how are we going to use this? How can we learn what the regulatory status is? How can we learn about insurance, about shielding, about containment, about operations, about all the various things that we need to do? That's the Convoy Corporate Program. It's open for all of you to look at online and potentially join if you want. That's the basic of that starting of that academy that builds the workforce and creates, if you like, that long-term generational training that's needed for the quality and the safety culture of this program. Next slide, please. Business and operating. Finally, these are built. Finally, this is set out in the market, and we've got the workforce to development. Now, the customers are stepping forward. Customers will then be able to take either a lease on a nuclear-powered ship, so it'll be controlled by an SPV, controlled by a set of investors that are sitting there as part of our program, if you like, leased out to customers. The big container shipping lines, the big tanker companies, the big grain houses, etc., can lease the ships over longer term. Or they can be operated in a joint venture, where you are getting into the, if you like, specific cargo operations, say a mining company and a steel mill that has a supply chain of iron ore moving between them. You have that joint venture with the shipper and the receiver in that value chain of that commodity where the ship sits and operates as the conveyor between the two. Floating nuclear power plants, same thing. You can sell them, you can lease them out, you can operate them in a joint venture with the customer as they go. Each particular project solution can be tailored to one of those customers depending on what they need. And the financeability of those special purpose vehicles that owns each one of these units is individual. You can tranche that through equity, through debt, through financing, export control guarantees, etc. So there is a lot of options here, and we see now the customer base starting to step up and say, okay, how does this apply to us? How do we do this? How do we get this? How do we get this contracting strategy in place to do it? Again, that's something that we're working on right now and should be bringing you news about in the coming year. Just going to finish this off with a little bit of an insight into what's happening in the regulatory side of this. There are two critical things that I'd like to talk about, and the first one is really, the standards regime around this. So standards are set in the maritime industry by the International Maritime Organization. In the nuclear industry, it's set by the IAEA, the International Atomic Energy Agency. These are member states getting together and agreeing on what safety standards, security standards should be for this industry. Nuclear-powered ships has been part of the safety standards for shipping since 1981. In the 1970s, there was complete agreement among all the member states of the United Nations, so the International Maritime Organization, that nuclear-powered ships were coming and we needed safety standards for them, and they put together a very comprehensive code of safety rules for nuclear-powered ships. But since then, nothing has really happened, because the technology that was selected for that particular regulatory review was the naval reactor. It was the one that was used on submarines. It was the one that was used on warships, the one that we cannot insure, and as a result, nothing happened. Now we're revising this standard, and we've spent years building the gap analysis and the critical sort of understanding of what needs to be done to the standard to bring it up to date from early 1980s to a modern day with all the rules and regulations we have today. And that is something that is now actually happening at the IMO. We believe and we hope that nations, including the United States, is now going to take this forward in the summer and propose this as a key piece of work that gets done over the next 4 or 5 years. Similarly, at the International Atomic Energy Agency, the Director General has started a new program called ATLAS, Atomic Technologies Licensed for Applications at Sea, ATLAS. That is a new, not quite a division, but a new sort of group inside the IAEA that is going to drive forward the nuclear standards, nuclear safety standards, security standards for how maritime gets done. as a unique new initiative that links with the International Maritime Organization to create that framework that we need as a foundation for all of this. In order for that insurance policy to be written for nuclear-powered ships, we must have a convention. We must have a liability convention, which means that if you have a US-flagged vessel sailing to a foreign country, say it comes to our place in the United Kingdom, and something happens and it needs to make a claim, it needs to have the UK signed up to that convention. So you need this network of convention partners from member states that agree to an insurable regime for nuclear-powered ships. Now, this was tried in the 1950s, and in 1962, just 9 months after the Cuban Missile Crisis, 50 nations were going to sign a new treaty called the Brussels Convention. And on the 25th of May, they met in Brussels, and they were going to sign this convention, which was going to change nuclear shipping or bring nuclear insurance to this fledgling new sector. But there was one disagreement. Remember, amongst these 50 nations, only 2 had nuclear ships. They were the Soviets and Americans. And only those 2 could really dictate what was going to happen. The Soviets wanted warships included. The Americans said, no, we don't want warships included. And it fell apart. They walked away. And since 1962, nothing. But the work that had been done prior to that is very good. So what we're now doing is we're bringing that convention back to life with the insurance industry, on the nuclear side, on the marine side, with the underwriters, with the syndicates, with the reinsurers, and with the individual state departments of those countries that need to be involved in this to recreate that framework of a new insurance liability convention for nuclear-powered ships. And we believe that we can have this on track to be done if it's done outside of the OECD and the IEA and the IMO, etc., already by 2030. So these things come together into a regulatory regime, an insurable regime, and the technology being brought to market. This is happening right now, and it's an important piece of work that gets completed in about 5 years. And with that, ladies and gentlemen, I'm going to say thank you very much for listening to me, and I hope you have a fantastic day. And yeah, thank you.